No, no. and saying that not everybody was able to go to the field, so I'm going to give you some extra points, but not too many because it's unfair to the people that couldn't go to the field.
Okay.
At least it will help.
So is it as extra point or we have to do something what we have so far?
Just submit it, and I will decide it later.
Okay. We have to submit what we have.
Whatever you have. And I need also evaluations of the members of the group.
Okay, because I don't see anybody talking about this one because we did the one we had the individual one we did already, but I don't hear. We went to the visit. The visit is here next to my house. I can go there too, but I have some pictures, but we never talk about it, so we have to start writing about it.
Yeah, because the semester is almost over.
Yes. So I will email them. We have the group meet, so I have
that is leadership.
Thank you very much. So that's it. Professor.
Yeah.
No, also, just only the summary or the PowerPoint?
Everything, whatever you have. Don't spend too much time. You need to study for the final, whatever you have.
Okay, thank you. So can I do mine or still we have to do together?
Well, it's a group project. You want to do yours because the other people didn't go to the field.
So they went, or everybody went there. But you see, as an example, we didn't talk about it. So I don't know.
If you don't have it ready, don't spend time. I prefer you spend time studying. It's more important.
Okay.
You made your decision.
No, I would like to write something because already we have the information, like the picture. It is not far from where I live, but I don't know the other people. I don't know. I don't have any idea. We never talk about it.
Talk to the other people, but don't spend too much time because the final is approaching very fast. You need to study for the final.
Okay, so I will email them. We will see what will happen. Then I would like to do something. I don't want to. I don't. To be honest, I didn't do anything so far for that.
Okay, whatever you think is the right thing, do it.
Okay, thank you.
Okay, look, just wait until everybody gets in. I want to talk about the finance. Thanks. Yes, Nathan, I will have office hours. Just let me know what time you want to come to my virtual office. I had chocolates and Coke and everything. Okay, well, good morning, everybody. Um, this set of homework problems are due on Wednesday next week. So this is the last set of homework problems that I'm assigning. So this is due on Wednesday instead of Monday. So this is the last one. Also, as you already know, it was not me, it was the university had changed the time and the date of the exam. Everybody knows that now that the exam is the 11 at 11. It's only an hour and 50 minutes. So Luke was asking, how we're going to set up the exams and we only had hour and 50 minutes. So I'm going to give you two problems in the final exam. I am writing the problems, and the problem that will take me the longest to solve, I will give you the longest time. So probably one problem is gonna be an hour and 10 minutes, and the other problem is gonna be 40 minutes because we only have an hour and 50 minutes. I'm gonna design the exam for you to take less than that time, but usually some of you are slow. But we had no choice. We had to follow the schedule and the time. I cannot give you more than 1 hour and 50 minutes. You need to look at the other courses because many of the professors, they do not know that the university had changed the date and the time. So it should not be any overlap in your final exam. It shouldn't. But if you have any overlap, go and talk to the other guy because I was the first one that told you about it. Any question before I continue? Yes, out of 100. And also some people ask about the project. So the field visit, it is impossible to have that report ready because many of you didn't have the time to go to visit. Many of you were ready to go to visit. So whatever you have, send it to me. and I will try to see what I can do with that. But whenever you send me the field visit report, don't spend too much time on that report because it is important, more important that you spend your time preparing for the final exam. And if you do send me, you upload the field visit to my personal email, I want you to send me the evaluation of the member of the group. I want you to give it an A, B, C, D, F, whatever you consider the right grade, and put the reason why you're giving that grade. Any question? What 5-point bonus? What are you talking about? Hey, FOMO. What are you talking about? FOMO? 5-point bonus for what? Okay, I don't know what he's talking about, but I forgot to tell you. The first exam is 30% of your final grade. The second exam also 30. The final was going to be 30, but since we only had 2.5 for the internet project, so the final is going to be 32.5% of your final grade. So the final is going to be 32.5 of your final grade. Any question? Okay. One of the homework problems that is due today, they gave you the wind uplift. The wind uplift is negative. So in the low combination, it goes as a minus. As you probably figure it out, for that problem, the combination that control the design was combination 3. This is in chapter 2 of the textbook. And I gave you a copy of this page at the beginning of the semester. Probably you already forgetting about that. But for that homework problem, this is a low combination that control. And you have to be careful because, for instance, 1.6, the live load of the roof, or there's no or the ring. So in here, or. The same in here, 0.5 of the live or 0.5 of the wind. So this in here could be several cases depending on the loading, but this or in here means that you cannot use those two together or three together. This or that, that what the or means. So several people ask me about this. I just want you to understand that the wind, the way it is given in this problem is a negative pressure because it's trying to uplift the roof in the opposite direction that the gravity load. But don't forget that this is why you have to look at the 5 possibilities, and it's not in the code. They remove it from the code, but it's in your text. I'm going to finish today what we were doing last week, and after that, I'm going to start doing beam cone. Somebody asked me during the weekend if for a standard section, do you need to compute the L sub P and the L sub R? If the section is standard, you just go to chapter 3 to table ZX and you get from there the value of L sub P, L sub R. Some of you that they're taking the course again because you like this course, but I didn't teach last semester. Last semester, they were computing the value of L sub P and L sub R all the time. If you have a standard section, you just go to chapter 3, table ZX, and you find the value of L sub P and L sub R. So this is the last case that I'm going to do, and this is a beam that had lateral support every 15 feet. I saw this beam before we continue lateral support. So if you look at this problem and compare with the problem in the previous chapter, exactly the same. The only difference is that now the lateral support is every 15 feet. That is the only difference. So the answer, of course, is going to be different. But this is a typical built-up section. I know that 99.99 of you know that this is not in the code. But the 1% that doesn't know, I want to reiterate, I want to tell you again that this is not in the code. This is not a standard section. So everything that we need to solve a problem, it has to be computed. And this is very simple. There are 3 plates, and this plate is 16 by 1/2. This is 26 by, what was the dimension of this one? Let me see. Also the thickness of this is 1 inch. Of the web. And so in here, the area in exam number 2, nobody had a problem computing area. This in here is the density times the area divided by, in here there is a mistake. It should be 12 square. The answer is correct. This is 0.143 kg per foot. So this is the weight of the beam. And in this beam, there is a load like before the PU. So this reaction is PU divided by 2. So the moment is PU divided by 2, but L in here is 45. So this is L to B. This is L to B, and this is L to B. We already discussed this before. The critical section is going to be the one in the middle because the largest moment, or both of them. And MU is the one produced by the point load, and this is the one produced by the weight of the beam. It's a large moment. I to X, no problem. Couple of you have problem computing I to X for example number 1, and I don't need in here too many computations, but I do need I to Y. R to X 10.09, R to Y 2.86. This was a new computation ZX, and just to refresh your memory. To compute this, the ZX value, we divide this into 2 sections. So it's going to be this area and the distance from the centroid to the neutral axis. This area, the distance from the centroid to the neutral axis, times 2. And this is what I did the other day. Always, this is the plastic module. The elastic module is IX over liter C, and liter C is this value here. For the compression and the tension, the same value. So what we had in here is the plastic and the elastic module. Always this is larger than this value, because like I mentioned the other day, the ratio you divide this by this value give you the reserve capacity, how much the moment will increase when it becomes the plastic moment. And by the way, this number divided by this number is called the shape factor, letter F. We always need to check the flanges and the web. In this case, there is the value, the 16 is smaller than 8.02. So not good. It means that we had a problem with the flange. If we look at the web, H over TW means that there is no problem with it. So I was saying the other day, and I want to point out again, don't get confused. They asked me during the weekend about this table. Remember, this table B41B is for the beams. The previous one, this table in here, this is for the column. So for the column, this is lambda, this is lambda sub r. But for the beam, whenever we look at this, with all of this is lambda sub p, lambda sub r. So our value of lambda is larger than lambda sub p. We need to compute lambda sub r. But our case is this one, because this is a built-up section. In the exam number 2, some people are using the one on the top for the built-up section. This in here is for a standard section. This is for our built-up section. So we have to find the value of K to C, that most of you know where to find it, and the limitation. F to L is a new value, and I mentioned the other day in here that they ask you, this is the section, elastic section module for the tension side, and this is for the compression side. I asked you the question the other day, and you gave me the correct answer. In our case, because of symmetry, is equal to 1. So don't forget that this table is for B. So here on this page, and on page 20, I computed the value of lambda sub r at 20.90. This is the value of K sub C that you computed before. And so we had our situation that our lambda for the flange is larger than lambda sub P, but the more lambda sub R. So this is the equation that controls our design. And this in the code is page 16.149. And I asked you before that don't forget to put in here as lambda sub P is smaller than lambda sub R. This is the formula that control. And of course, this is going to be smaller than M sub P, because from M sub P, you're subtracting all of this value. And be careful with your computation, because sometimes we are not paying attention and it comes larger than N sub P. It cannot be larger than N sub P because we're subtracting from the plastic moment all of this. And I'm going to go back to one of the homework problems, because during the weekend they also asked me the question. One of the homework problems that is due today, this came larger than lambda sub. When you go to the chart and you hit the curve that is going to give you the answer, you're going to see that it's no longer horizontal or a linear equation, it becomes a parabola. So by looking at a parabola, you're going to know which equation control. But whenever we had the value, like in our case, homework problem, that this was larger than lambda sub r, means that the elastic equation will control. And please be careful, because in the past, in a final exam, I'm given a problem that requires you to use this equation. And this equation, the critical stress is computed by using this value, because we are designing a beam. But in that final exam, many people, instead of using this value for the critical stress, they went to the previous chapter. And they use this equation to compute critical stress. Why for the homework problem we cannot use this equation? Why for the homework problem we cannot use this equation? Anybody? Because this is for economy, and that is correct. But in that final exam, many people, and I went through the same that I'm going through today, and asked the same question, they gave me the right answer, and in the final exam, they used the wrong critical stress. They went to the back of chapter 4, and they found it not. So, just a clarification from the homework problem that is due today. So, what it means. I do know that you're trying very hard. I just want to share this information with you because it's not only because we had online exams, online lecture when we were face to face. The same problem I repeated 100 times that, and they did the wrong thing. So look, whenever we had a beam, the lateral embrace, there are three equations, and these are plotted for you. In when embrace length is smaller than L sub P, this equation control phi m sub n equal to m. Whenever we are, most of the homework problem fall between L sub P and L sub R, this equation control is a linear equation. And so that is the one that uses C sub P. But whenever we had this equation, when embrace length larger than this value, this is the equation that control. This is the equation that had a critical stress. So please don't make the mistake. Well, this was just a clarification for some of you. And so going back to this problem, this is the equation controlling our design. So when I did the computation of M sub P NYCF divided by 12. This is not in the code. This M sub P is not in the code because this is a built-up section. So you cannot find this in the code, built-up section. But we already had a value. This is ZX, Fy divided by 12. This is my plastic. M sub R 0.7 FYSX. We already computed this value because IX divided by little c. You can see in here that they always larger than this value. Always check your number. And this is the nominal design or the design strength, nominal strength, M sub P minus M sub R, lambda minus lambda sub P, lambda sub R minus lambda sub P. And replacing value in this equation. So in here, I replacing the value, it came 1528.85. So we have 0.9 times that value, it gave me the design strength, PM to N, equal to 1375.96. It has to be larger than M sub U. So whenever we had a problem With a flange, the code requires you to check lateral torsional backline too. You have to check. I'm going to go back to the code 16.149. In this page, we have this formula. This is the one that I just used. But also the code requires, look, lateral torsional backline shall also apply. So whenever we have a problem with the flange, we also need to check lateral torsional backline. We need to check both of them. And the smallest number will control, because that means that if this control never will reach this value. If this value of control never will reach the value. So remember, you have to check both of them. It says in here, but sometimes you forget. The same example talking about, people did check and forget about this one, and this one was controlling the design. So whenever we do lateral torsion backing, we have to find lines to build up and standard section. But for standard section, we do not have to worry, because this value L sub P has already been computed for you, chapter 3, table CX. So chapter 3, table CX is very important for the final exam. And the value, if we are on the same page, the value of L sub R is given in here. And the value of R sub TX is indicated in here. And also is the value of C sub W is indicated here. So don't forget that you have to divide this by 12. A lot of mistakes happen because you do not check your unit. So don't forget you need to divide this by 12 because it's in feet. They have to divide by 12 because it's in feet. Last semester, they were doing everything in inches. So be careful. If you have experience from last semester, be careful about the chapter, the last chapter. So 12 and 12. So I had computed L sub P in here because we had E, we had FY, we already computed it. In the previous pages, we computed R sub Y, and you have to divide by the 12, 80.86. I had to compute L sub R because our value is going to be between L sub P and L sub R. So this is the equation I just shown to you. This is page 22. The value of letter C is equal to 1. Here's the page where you can find it in the code. This is not in the code. You need to write this formula. And I know that you're familiar with the formula because some of you used this formula in exam number 2. You were not supposed to use this formula because we had a continuous support, so I don't know why you were doing torsion. No. So, but this formula is 1/3 of b times t cubed. I computed this at 10 inches to the cube. This came from the code R sub t. We had I sub y. This is the clear distance between the flanges. We had this value. And I put in here also that this is the distance between the flanges centroid. And uh, whenever we look at this value, we had L to R 2896. So this is the most important thing. The brace length for our problem is larger than 8.86, but smaller than R. So this is the equation of control. This is what we need to compute C sub B. So sometimes we don't have to waste our time computing C sub B. Only if we had lateral torsional vacuum, depending on this comparison, we need to compute C sub B. Since the center portion of the moment, the center portion of the beam is the critical, we have 1/4 is 18.75 from the left, 1/2 is the center, 3/4 because symmetry is also 1875 from the right, and our span that we're looking at and brace length 15. So here I'm saying M sub A in here because symmetry is equal to M sub C. So I had a value 9.375 pu. I computed C sub B. And just to give you an idea, sometimes you look at this and you know which is the value that this C sub B should be. And here is about 1.09. I want to show you something that I promised last time and I forgot. Go to chapter 3, page 18. Go to chapter 3, page 18. So just as a reference, because I want you to do your computation. But in here, for lateral bracing, it gave you in here, for the load and mid span, we know braces 132. So this table is a table that you can use to check your value, the value of C sub B. Right? If you look at this case, for instance, the moment diagram for this case is going to look the moment diagram is going to look like this. So this is the center portion. So this is to be equal to 1 because it's constant. That's why in here, if you look at this portion, is 1. This portion, because this is the shape of the moment diagram, non-uniform. This is C sub B. M sub P, M sub P, M sub R. This is L sub B minus L sub P, L sub R minus L sub P. So in here, it came at phi m sub n 1765.82. So if you look at based on lateral torsional backlink, you design a strength 1765.82. Based on the flange local backlink, the 1375.96. So this was the flange local backlink, 1375. This is based on lateral torsional back. Which one is controlling our design? The flange local backlink or lateral torsional local back? Sometimes it is the other way around. Sometimes it's the other way around, so you have to do both. So since the flange is controlling our design, we made that moment equal to M sub U. From here, we found PU. And then information of the problem is 25% is the dead, 75% the live. This is the answer. Do I need to include the weight of the beam for this problem? Do I have to revise my moment? Anybody? Do I have to revise my moment like I had done in the past? No, because I already computed the weight of the beam because this is a built-up section. Any question before I go to the final chapter of this course? So remember, built-up sections, they are not in the code. So based on the geometry, you have to compute what you need. And what you need, I sub X, I sub Y, the gross area, Rx, Ry. For a standard section, they have been computed for you in chapter 1 and also in chapter 3. But you have to compute it here as L sub P and L sub R to see which equation controls this. So now I'm going to go to the next chapter and the final chapter. Is our if L sub B is greater than our L sub R, when we compute critical, can we tell on the next page during the exam? Says use a node at the top left. Okay. Well, Amir is asking about in here considering C sub B equal to 1 because he says the code said that you can do it conservative. I'm glad that you read that because I said before that I want you to compute C sub B in this course. Whenever you get your degree, I know you're going to be a great engineer. You can assume this C sub B equal to 1 because it is conservative. And here, you're learning how to compute C sub B, always. Okay, any other question? In the room, we just saw a PS is maximum service law. Okay. The question about the service law. Right. So, look, this P/S is the service load. And for this service load, the live load is 3 times the dead load. Whenever we talk about the service load, PS is equal to D plus L. So whenever we talk about the service load, portion of the service load is the dead load, portion is the live load. So the PS in this problem stands for the total service load. The PS in here is the total service load, that it is the load by three times. The load plus the live load, and the live load is 3 times the load. Any other question? So this page comes from our textbook, but what we're going to be looking at, we're going to combine the bending and the axial load. And in general, it could be bending combined with tension or compression. In our case, it's going to be combined bending and compression. So if you remember from mechanical solid, in mechanical solid, I think that some of you took that course last semester. In mechanical solid, we learn about stresses, axial stresses, shear stresses, bending stresses. But the bending stresses and the axial stresses, they are called normal stresses. So just to give you an idea, something that we know and you also know. If this is a typical wide flange, bending stresses. So normally, this is letter C, the normal stresses, it means that this point in here, this point in there, that point in there, all of these points, they have the same stress. And the stress here, sigma is equal to MC over I. And the stresses are perpendicular. They're called normal stresses. Bending stresses are normal, perpendicular to the cross section. This stress is acting in here, perpendicular. This stress in here is acting in here, perpendicular, normal stress. So if I had this situation, plus an axial load, I'm going to put an axial load compression. All of these stresses, sigma, they are the force over the area. And using compression. All of these stresses are uniform, and they're the compressive force and the compressive force divided by the area. So whenever I want to find the stress at this point, the stress at this point here, it's going to be, the stress is going to be equal to MC over I plus C over the area. So whenever we look at the stress at this point, it's going to be this plus this. So we add this, the stress due to bending, M0I, and the stress due to compression, C over the area. So what happens if I do the same at the bottom? What's going to happen with this formula? What's going to happen with this formula? If I do this one and this one, what's going to be the difference between the sigma at the top? Negative. So in mechanical solids, we show you there's a plus or minus. What is important to remember is that when you add the stresses produced by bending and the stresses produced by the compression, the maximum that you can use is the full capacity of that section. So you cannot use 150% of the capacity, so everything is limited to the full capacity. So you're going to see that the code does this in a very similar fashion, but they put smaller than equal to 1. Why did they put smaller than equal to 1 in here? Why do they put this and this is more equal to 1? Why are they using the 1 in that, in the code? Anybody? Make that up. Any answer? Okay. Well, you don't know, because we cannot have 100%, more than 100%. So this one means that we're using the bending capacity and the capacity due to the compression cannot exceed 100% of the capacity of that section. This is what they're going to mean. They're going to write the equation a different way, but you have to always remember this. Right? So there is going to be capacity due to bending. So we're going to find phi m sub n. There's going to be a capacity due to the axial load, phi p sub n. And the capacity that we use with bending and compression cannot exceed 100% of the capacity to resist the load of this cross section. So that's a simple way of putting what we're going to see. So in the old textbook used to be chapter 2. But this is combined bending and compression. And whenever we look at this, this is the situation that we're going to be looking at. I want you to look at this very carefully. This is called a beam column. So from now on, we're going to be making reference to the design of a beam column because it is behaving like a beam and behaving as a column. So everything that we learn about a column is going to be applied to each other. Everything that we learn about a beam is going to be applied to each other. And the way you saw your homework and if you have a question, I know that you understand the difference between a column and a beam, and I know that you know how to design a column. You did it for the exam. You know how to design a beam because I have seen how you solve the homework problem. So this is a load producing bending, moment bending stress. This is a moment also producing bending stresses. Sometimes we're going to have only this producing bending. Sometimes we're going to have only this producing bending. But we have to have an axial load to produce compression. So this is the typical beam column. And whenever we look at this, there's going to be a span. There's going to be lateral bracing. And also, we're going to have embrace length, the same that we done for a beam. We're going to do it here, the same we done for a column. But what's important to understand here is that there are going to be this deflection due to the load. It's going to increase due to the axial load. Because whenever you put axial load, this member is going to try to buckle, and the buckle is similar to a deflection. So now we're going to have a increase in the bending moment due to this axial force having some eccentricity. So there's going to be a primary and a secondary bending moment. The secondary bending moment is going to be called the P times a little delta, because the P large delta, that is the lateral movement for a frame, that's the side sway. So it's going to be P times the little delta. But the biggest point that I want to make today is that the moment is going to have the moment produced by this low, moment produced by this moment, not necessarily have to be the same. That's why M1 and M2 is going to be a secondary bending moment produced by the axial force times this deflection. And the code handles this secondary bending moment produced by the axial load by magnifying the original moment. So we're going to be computing a magnifying value for the moment. We're going to increase the moment times a magnification, the moment times the magnification factor due to the secondary bending moment. To make things easier, they had removed the moments at the end. They call the primary and secondary bending moments. So there is a primary bending moment produced by the given loading, and there's going to be a secondary. You see, you have it here the primary due to the bending moment, and the secondary due to this low time the eccentricity Py. So the secondary bending moment is going to be handled by the code by increasing the primary moment. So this moment is going to be multiplied by a magnification factor. This is going to be one of the typical problems. We had an axial load, we had a uniform. You have to be very careful, because in the final exam, like in the previous exam, I gave you the bonus that had a tension member and eccentric. You had to look at the load and determine what is this load doing to my member. And here I had a bending moment, a axial load that is produced in the secondary moment, but what I have is a beam and a column. So this is called a beam column. I'm going to stop here because tomorrow we had a long day. Tomorrow is going to be very important. I'm going to go over how to solve this problem. And it's going to be different than the way the solution manual does it. And so I'm going to show you step by step how to do it. I'm going to stop here. I'm sorry too long today, 1 extra minute from your time. Any question before I turn this off? Okay, no questions, so I'm going to turn it. Oh, yeah. Binaha, what's the question? So secondary moment is from the axis. Correct. Because see what happens. If you ignore this load, we're gonna have a deflection. If we put this load, I don't know if I can do it in here. If we put this axial load, this is gonna bend due to the axial load. This is what we call backlift. So the backlink is going to increase the deflection. We're going to have this force times this deflection. That would be the secondary bending moment. But it's going to be handled by magnifying the original moment. Exactly, from the axial load times the secondary. You don't need to compute the deflection because the code is going to give you a magnification factor. It will take care of that. Any other question? Any other question? All right, we'll see you tomorrow at 8:30. And therefore, you want to talk to me, just give me 10 minutes and I come back. You're welcome.